Thank you so much, everyone, for joining us today. Um, Before we start, I just want to introduce our DC-MUSE Center. We're a consortium of faculty members, scientists, and industry, all really focused on finding ways to electrify the chemical industry. And we want to thank the Sloan Foundation for sponsoring us and funding our research, as well as helping support these seminars. These seminars are part of an ongoing DC-MUSE webinar series to sort of talk about topics related to and tangential to this goal of electrifying the chemical industry. And we encourage all participants here to connect with us to stay informed about future webinars. And you can also go to our LinkedIn and our YouTube and watch previous seminars on topics related to decarbonizing chemical industry. Um, and so today we have a really exciting topic, which is the role of electrochemical carbon capture in the electrification and decarbonization of the chemical industry. And we're going to first start with Yayuan, who's going to give a talk on some of the more on some of the really cutting edge science that's been coming out of her group on in electrochemical direct air capture. Yayuan is a professor at the Department of Chemical and Biomolecular Engineering at Johns Hopkins University. Her research group works at the interface of chemical engineering, material science, and electrochemistry, and she really focuses on efficient and sustainable chemical separations. She earned her Ph.D. in material science at Stanford and did her postdoc training at MIT. She has won multiple recognitions for her for her research, such as the NSF CAREER, the Beckman Young Investigator Award, the Packard Fellowship, the ECS Toyota Young Investigator Award, and the Sloan Research Fellowship. So I'll let Yaiwen take it away on her work, and then we'll introduce our industry person after Yaiwen has presenting. Great.
That's good. Let me share my screen. Thanks, Justin, for the very kind introduction. Um, it's loading. All right. Okay, so today I'm going to share with you some of our recent work on using electrochemical methods for direct air capture, and with a focus on material and interfacial design and engineering. So just a little bit of background, I think. Before I start my presentation, I want to really thank my talented group of students who really made our research possible. And this work is I will be presenting is sponsored by Total Energies and in collaboration with Jeff, who's going to give his perspective after my presentation. So we have all seen some figures similar to this at this point, hopefully. So what can we do about climate change, right? So lots of things, but first and foremost is that we should reduce our greenhouse gas emissions. So academics have put together many pathways towards what we call net zero or net negative emission scenarios. So a large part of it is conventional abatement technologies like switching to renewable energies, and also capture carbon dioxide from large stationary scale emitters such as cement, power plant, and steel making industries, followed by storing them underground. So that's part of carbon capture, utilization, and storage. But in order to achieve net zero, there's also a big need to capture CO2 directly from the environment, either through air, that's what we call direct air capture, or through ocean to account for legacy CO2 emissions so that we can achieve net zero. So the overall take-home message for this kind of climate change mitigation scenario is that both capture CO2 from stationary emitters and dilute source are critical for achieving net zero, and there's no silver bullet technologies, but instead we need a wide portfolio of different technologies in order to do that. So with that, I wanted to, jump to our main topic today, which is direct air capture. So the current methods, the most mature methods for direct air capture is to use a bulk phase alkaline solvent. The reaction is pretty straightforward. Usually we'll use an aqueous solution of alkaline, in this case, potassium hydroxide, and then we'll send them through a large air contactor to blow air through the bulk solvent and to promote the acid-base reaction between carbon dioxide and potassium hydroxide and form potassium carbonate. And then in the incumbent thermochemical method, we'll have a pilot reactor to go through what we call calcium looping step, where we regenerate our potassium hydroxide using calcium hydroxide. And then in this case, we'll form a calcium carbonate as a byproduct. And in order to recycle the calcium, we'll send it through a calciner at usually 100 degrees Celsius to bake a pure CO2 off and regenerate calcium hydroxide to complete the whole loop. But the challenge is that this process is really energy intensive because of this high temperature calcination step. And a lot of scientists are trying to do is to replace the thermochemical method with electrochemical regeneration of potassium carbonate into potassium hydroxide. So the idea is to use electrochemical method to generate protons, either through hydrogen oxidation or water splitting or some other equivalent method, so that proton can react with potassium carbonate to release carbon dioxide, and followed by the simultaneous generation of hydroxide and to regenerate our alkaline sorbent. Now, the challenge for electrochemistry method is that electrochemical regeneration has no selectivity. So the proton generated can either react with what we are trying to get them react, which is carbonate and bicarbonate, but they can also react without selectivity with hydroxide in this alkaline solution. So that really gives us a challenge because bulk phase alkaline solvent in our state-of-the-art air contactor is really not very efficient. Because of the really dilute CO2 concentration in the air, the hydroxide utilization efficiency is roughly 10%. Meaning that if we send 10 hydroxide ions into our air contactor, only one of them get to react with carbon dioxide, and the rest of them will remain as hydroxide. And that would really limit the electrochemical efficiency when it comes to regeneration. One can argue that we can improve the air contactor design, but really, the incumbent technology, which is this company called Carbon Engineering, is trying to do, they already kind of engineering optimize their contactor after 100 person years. So there's really a limited way that we can do. So in order to make electrochemical regeneration more effective, there's one solution that people are trying to explore is to really use non-conventional air contactor design. And one of our colleagues, David Sinton in University of Toronto, has recently proposed this really elegant idea of using a crystallizer as your air contactor. So in order to, instead of using a solution-based absorption method, this design uses this kind of stranded-like contactor and very concentrated KOH solution to form potassium carbonate crystals. And these crystals can be harvested as a solid and directly sent into electrochemical reactor to get regenerated. So in this case, we are regenerating carbonate without regenerating hydroxide. And also, another alternative solution is that we can redesign the electrochemical cell to eliminate the need for air contactor to start with. And this is what we are trying to do through this research. So a little bit of an overview of our proposed working mechanism. So in this side of an electrochemical reactor, where we call a DAC cathode, we're sending in our air directly into the electrode through a gas diffusion layer. So basically, we're using the abundant oxygen in the air as a source to in situ create hydroxides through oxygen reduction reaction. So oxygen get reduced to form into hydroxide so that we can generate a very high concentration of hydroxide at the local gas liquid interface. And that very high local alkalinity can promote the rapid reaction between this hydroxide and carbon dioxide from air to achieve carbon capture. And then later, after the reaction, this carbonate species will get transported across an anionic selective membrane and get regenerated to release pure CO2 at the anode side of the reactor. And at this anode side, we're using what we call a proton-coupled electron transfer mediator or PCET mediator, which is in this case a small molecule that can reversibly exchange proton with electrolyte upon electrochemical trigger. So this proton release can react and acidify this carbonate and release a pure stream of CO2 without the need of downstream purification. And this reactor can later be regenerated through a reverse reaction to get protonated, and that is done through another smaller scale electrochemical reactor. And as we said, these because of the low CO2 concentration in the air, what we really wanted to do is maximize the utilization efficiency of hydroxide generated at the air electrode interface. So the unique invention of these work is to really introduce this interposer layer, what we call, which is a three-dimensional layer that is porous, so the air can permeate through, but also at the same time, it has anionic conductivity. So basically what it does is to increase the residence time of this hydroxide through this interposer layer and give this hydroxide a little bit longer time to react with the dilute CO2 in the air before they get transported to the other side of the electrode, electrochemical cell and get released. So a big design principle for this interposer layer is that it has to be gas permeable and it has to be anionically conductive. So what we designed is that we take commercially available anion exchange resin beads, which are these spherical particles like this, and we mix them with some sort of a porogen to create porosity, which in this case, we chose the simplest one, which is sodium chloride crystal. You can see this kind of cubic shaped sodium chloride. And then we mix these two together, we grind them, and then we add some sort of polymeric binder to kind of glue them together. After grinding, we can put them into a plastic mold to shape them in whatever size and thickness we want, followed by thermal treatment, a quick hot press. And then we can put them in water and wash away the soluble sodium chloride porogen, and then we can get a standalone ion exchange wafer. And this resulting wafer is very mechanically robust. This is the student bending this wafer, showing the good mechanical stability. And the important thing is that by tuning the resin and sodium chloride porogen ratio, we can really tune the porosity very precisely in this kind of wafer. So this is a cross-sectional image of the resulting wafer material. And as you can see, as I change the porogen content, which is a theoretical pore volume introduced by the porogen, and compare with this X-ray chromatography determined porosity, they show a pretty good agreement, so indicating a good tunability of this material. So with this interposer layer, we went ahead and tested the carbon capture performance using 400 ppm CO2 plus 21% of oxygen mimicking the air condition. So without the interposer layer, which is only the oxygen reduction catalyst along with the membrane, you can see the capture efficiency is really low. So the capture efficiency here is defined as how much carbonate is being formed versus how many hydroxides being produced using our electrons, right? 100% carbon capture efficiency means that all the hydroxide electrochemically produced are reacted with CO2, which is what we want. So as we introduce only the resin beads, so not the wafer yet, you can see because the resin bead occupies some of the volume to increase the residence time of the hydroxide, you can see a slightly increased CO2 capture efficiency. But once we introduce our wafers with varying porosity, you can see a drastic improvement of capture efficiency, especially at the lower current. And there is a dependence of the performance with respect to the porosity, right? So as we keep increasing porosity to allow more air to come through, the performance gets higher, but there's a limit. So if we further improve the porosity, the performance decayed because we don't have enough anion conductive pathway for the hydroxide to percolate efficiently through the interposer layer. So this is really promising, but as you can see, as we increase the current density, all this performance kind of converge to a lower value. So we think fundamentally there is some limit there, which we attribute to the relatively slow CO2 solubilization into the resin, into the solution phase from the gas phase as we increase the current density. So because of that, we introduce an electrochemical protocol, which is a pulsating our current. So we apply a current through a certain period of time to generate hydroxide, and then we stop the current to let the hydroxide transport and CO2 react, and then we repeat the electric current again. So without pausing, this is our typical performance. And as we do some pausing protocols, so this is 10 seconds on and 10 seconds off, we can see that our high current performance, the efficiency is a lot better at high current. So then we decided to use the best porosity resin wafer and then the pulse current to demonstrate our performance. So this is at 500 ccm CO2 air inlet flow rate and at different current density. So in addition to capture efficiency, we also care about how much CO2 is being removed from our inlet gas, right? So as you can see, we increase the current density, we can achieve about 80% of removal of CO2. Beyond this point, there's no reason that we keep increasing the current density because we're almost depleting the CO2 in the gas phase. In order to further improve the current density, we keep increasing the inlet gas flow rate to 1000 ppm, and then you can see we can push the current to about 50 milliamp per square centimeter with decent capture efficiency. And then how do we further improve the performance? What we discovered is that on top of the resin bead, we can also introduce a thin layer of coating of anionic conductive ionomer. So we tried two different kind of ionomers. One is called Sustanion, which is a commercially available ionomer, and the other one is a synthetic ionomer from our lab, which is called poly-DAC. As you can see, with the ionomer coating, we further promote the transport of hydroxide and carbonate in our resin wafer, in our interposer layer, and also improve the solubility of CO2 in our interposer layer. So with that, we can further improve the CO2 removal at high current and the CO2 capture efficiency, which is really promising. And another advantage of introducing this additional ionomer coating is that we can reduce the fuel cell voltage at higher current density, and that translates to lower voltage or lower energy input. So with that, we want to compare our electrochemical DAC performance with existing literature. So really, we are demonstrating one of the highest CO2 capture efficiencies with current density at 1 order of magnitude higher than what's being demonstrated previously. And if you look at the energy consumption, if we pair our PCT mediator regeneration with oxygen evolution reaction, because of the higher overpotential of oxygen evolution reaction, the energy consumption is on the higher side. But alternatively, we can pair our regeneration with a alternative oxidation reaction. In this case, we're oxidizing biomass into value-added products, and that can substantially lower the energy consumption while give us an opportunity to generate beneficial co-products. And then we tested the long-term performance of our EDAC setup with a schematic shown here. And this is our device in the lab with 2 electrochemical reactors. So in one of the electrochemical reactor, we're sending air in and we're measuring the outlet CO2 concentration. So this is the DAC electrode sensor data. And on this other side of the cell, we're coupled that with PCET mediator, and we're monitoring the amount of CO2 being released through this regeneration step. So that's the mass flow meter data showing how much CO2, pure CO2 is being regenerated. So as you can see, over the course of, this is versus time. So the course is 50 hours. We demonstrated really consistent performance for our capture side. So we have a CO2 capture efficiency about 40 and above 85% of CO2 removal, and the performance is really stable. And as you can see from the CO2 regeneration side, we're constantly generating a very stable output of CO2 with the amount of released versus amount of capture being about 98%. So saying indicating indicating that this process is highly reversible. And we also evaluated our gas product using gas chromatography. As you can see, we only observe CO2 as the main product. There's no byproduct, so the product is really pure. And then, based on this very promising result, we also conducted a series of multi-physics modeling and trying to understand what makes a better interposer layer design. So I won't go into details, but basically there's a trade-off between the porosity of the interposer layer and the pore density and the applied current and thickness. So this kind of physics-based modeling can guide us to further improve the design of interposer material in our future work. So with our experimental data, we also conducted techno-economic analysis. So our base case is based on our real experimental data, and here are our assumptions. So our current capture cost is about $450 per ton of CO2, and there's a pathway for us to further improve the performance to achieve a more realistic deployment. So a big driver is the efficiency of the system at high current. So our current efficiency is about 57% at 50 milliamp per square centimeter. If we can further boost that to 80% through, say, a better ionomer design or better interposer material design, we can reduce the cost by about $100. And if we couple that with an alternative oxidation reaction of biomass upgrading, we can further reduce the cost. And the electricity cost is another relatively sensitive parameter. And then we can also lower our stack cost by using cheaper bipolar plate and whatnot to reach our target performance cost value. And we also kind of done a sensitivity analysis of our TA model by perturbing 20% of our input parameters. So similar as what we expected, the system is the most sensitive to the CO2 capture efficiency, and we can improve that through better material design, as well as current density and electricity cost. So we achieved on the order of 50 milliamp per square centimeter current density. But, one can argue that, this is still not, industrial current density that one would expect for electrolyzer, which is on the order of hundreds of milliamp per square centimeter. But we want to make the argument that for DAC, because of the low CO2 concentration in the air, we don't necessarily need to go to extremely high current as long as we're being cost competitive. So this is the kind of the overall cost versus the current density. As you can see, for our system, we are already hitting a pretty sweet spot, right? So keep increasing the current density does not necessarily translate to a better, a lower cost overall. But this is really promising data, but admittedly, there's a long way to go, and I look forward to hear Jeff's perspective on electrochemical DAC technologies. So with that, I want to thank all of you for your attention. I'm looking forward to questions and discussion afterwards. All right.
Great. Thank you so much, Yayuan. That was a really great talk to see, and that interposer work is super cool. Now I'm happy to introduce Jeff Parkey, who is going to be providing our industry perspective on electrochemically mediated carbon capture. Jeff is a senior scientist at Total Energies, one of the world's largest integrated energy companies, where he works within the CO2 techno hub, evaluating emerging carbon capture technologies to inform strategic investments for the company's decarbonization portfolio. His focus includes electrochemical approaches, which he evaluates through R&D partnerships with universities, startups, and industry consortia. And before joining Total Energy in 2023, he spent 20 years at Lintech, serving as a scientist and principal investigator on NASA, DARPA, and DoD projects spanning fuel cells, electrolyzers, advanced batteries, and electrochemical separations. So there's really no better person to be providing us this industry perspective. And so we're really looking forward to seeing what you have to say, Jeff. So without further ado, I'll let you get started.
Great. Give me 1 second. Okay, is a slide showing up?
You're on.
All right. Yeah. So yeah, I just
Jeff,
want to say thank you for inviting me, and happy to
Jeff,
be here.
I think
What?
you're on presenter view. You need to swap the.
Oh,
Yeah.
this worked a minute ago. Give me 1 second.
No worries.
We good now?
Yep, that's perfect.
All right. Yep. Sorry about that. Yeah. So as Justin mentioned, I spent most of my career doing kind of early stage technology development. I joined Total a few years ago, and so it's been kind of an eye-opening experience seeing from the industry perspective and the enormous scale and economics behind deploying technologies like direct air capture. So bear with me, I've got a couple of kind of corporate boilerplate slides, but I thought it was important to tell you a little bit about who Total Energies is and provide a little bit of context about the scales that we operate at. And so we're a multi-energy company. Traditionally, we've been oil and gas, but we're rapidly expanding to electricity generation. Just to kind of throw some figures out there, as of 2024, we were generating 41 terawatt hours of electricity. We're expanding that to roughly 100 terawatt hours of electricity by 2030. So we're not just oil and gas, and we're part of this energy transition that we're seeing across the world, right? We're a very large company. We have over 100,000 employees across 120 countries. And just kind of give you this sense of the kind of dollars that we deal with and the scale. We invested over $4.8 billion in low carbon energies in 2024. Our R&D budget is over $1 billion. Roughly 2/3 of that is focused on low carbon and decarbonization solutions, including technologies like DAC. So we're talking about massive scale across the world, right? So just a quick view of Total's energy transition strategy. So I won't spend a lot of time here, but traditionally we've been heavily oil and gas. The plan is to transition more and more to green electricity and low carbon molecules. That said, we still see a significant portion of energy production in 2050 still being natural gas and oil. But the idea is that long term, we want to reduce the carbon intensity of the energy we provide over time. And so part of this strategy is that we have a lot of assets across the world currently, right? And so we're talking about refineries, we're talking about chemical plants, natural gas production, et cetera. So our kind of near-term focus is decarbonizing these assets first. We're focusing on kind of the low-hanging fruit that is the most economic. So we're talking about efficiency improvements, minimizing methane leaks, electrification, and capturing CO2 where it's emitted. That's typically a much lower cost than something like DAC because CO2 is much more concentrated. So where we see DAC in this kind of portfolio of decarbonization options is that we know we won't be able to capture 100% of all of our emissions. And so we're still going to have a lot of residual emissions left over. So we kind of see DAC as sort of mop-up duty in a lot of ways, right? And we're going to have some assets, maybe like our offshore platforms that are too expensive to decarbonize through other means. And so DAC for us is an important lever to truly achieve net zero. And then even kind of longer term, DAC capturing CO2 from air, and then you can take that CO2 and convert it into synthetic fuels like synthetic aviation fuels, chemical feedstocks, and so on for more of a carbon neutral circular economy. Something we're evaluating as well. I think that's more of a longer term objective. So we're heavily investing in DAC R&D at this stage. That said, I mean, we see DAC as more of a longer term technology for us, so 2040 and beyond. Of course, that's subject to change depending on advancements in technology and so on. But just kind of give you a perspective of how we see DAC fitting in with our decarbonization efforts. So a big part of this as well is that even if you capture CO2 from point sources or through DAC, you need the infrastructure to store that CO2. So that's something we're heavily involved in. We've got a lot of CO2 storage projects, primarily in the North Sea and Europe, where a lot of our assets exist. But we also have a project in development in the Gulf Coast off the shore of Texas as well. So the Northern Lights project, just to kind of give you a sense, it's phase one became operational last August and can handle storage of 1.5 million tons of CO2 per year. So this is basically ship transport of CO2 from cement plants and so on. Then it goes through a pipeline, and then it gets injected very deep under the ocean into saline aquifers for permanent storage. But the point I wanted to make here is that beyond DAC, you need all the supporting infrastructure. Like you need the energy that you need to power the DAC system. You also need a place to store the CO2 you capture. So DAC economics, I think it's pretty well known that DAC is expensive, and a big portion or big reason behind why it's expensive is that CO2 in air is just extremely dilute. So this figure shown here, each of the gray dots is an air molecule. That one red dot, which you may not be able to see too well, is the single CO2 molecule you're trying to capture out of air, right? And so it's roughly a 2,500 to 1 concentration ratio. So talking about very much a needle in a haystack type of separation process. And that means you have to move a massive amount of air to capture CO2. It's, depending on the capture fraction, you need to move 1.8 million cubic meters of air to capture 1 ton CO2. Just to put that in perspective, that's like the entire air volume in a large NFL stadium, for example. And so because it's so dilute, it's always going to be energy intensive. I don't think there's any way around that. And that energy also drives cost, right? And so what we're seeing now is with the early stage kind of pilot deployments of DAC plants, that the costs are typically in the $400 to well over $1,000 per ton range. And, of course, the earlier stage smaller pilots are definitely on the high end of that, right? And just kind of illustrate the gap, the U.S. has a subsidy called 45Q that pays $180 per ton. And so, and that's a temporary subsidy. It's only good for 12 years, but it kind of gives you a sense of how much DAC costs have to come down for it to be economic at scale. And so I also wanted to stress the size of what we're talking about. And so our baseline design for a DAC plant, I'm talking about longer term here, is a million tons per year of capacity at DAC scale. So we're talking about a very large infrastructure project on the scale of like current refineries, for example. If you can sort of visualize how big and complex and expensive those systems are. Early stage plants will likely be in the $1 billion range. Those costs will come down as you deploy more and more plants, right? But just to give you a sense of how big we're talking about and how much capital it takes to really deploy at scale. And then based on kind of current energy consumption of DAC, you're likely looking in the 200 to 300 megawatt range of continuous power that has to be supplied, right? That could be renewable energy. It could be waste heat from data centers. There's a lot of options there, but we're talking about a massive power plant that also has to be built to power the DAC process. And so, if you look at a lot of, net zero scenarios where people are talking about doing DAC at gigatons, so billions of tons per year of capacity, we're talking about, 1,000 to 10,000 of these plants. So these are massive, expensive plants, and we need a lot of them, right? And so that's kind of the general scaling challenge behind that. So, I'm talking about how big the scale is, and I mentioned that Total Energies sees DAC as sort of a long-term thing, but I wanted to give a kind of an illustrative example of a timeline to make the point that development like research that Yayuan's doing, is highly relevant today. And so these numbers are made up, right? And so but they're kind of based on a typical timeline for deploying these very large infrastructure projects. So if you just set a very conservative target of deploying 10 million tons of DAC capacity by 2040, so we're only talking about 10 million, not talking about gigatons or anything like that, and you work your way backwards from achieving that in 2040, it means that we have to be making investment decisions for multiple plants in the mid to late 2030s. It means our first commercial plant's got to be in the early 2030s, which means we have to have a demonstration plant, in the early 2030s and pilot scale. And eventually, I mean, we're talking about we need to have a lot of work done at the lab scale pilots today, right? So it's a long-term strategy thing in terms of deploying DAC, but it is very much an urgent need to make progress today, was the main point. And, from our perspective, I mean, these are massive infrastructure projects. We're talking about lots of money. And so it's really about de-risking the technology, right, before we make those big money bets on deploying it. So this is kind of how I see what must be true for DAC to scale. So we're talking about full commercial scale DAC. There's I broke it up into two different columns. At the technology side, right, we need breakthroughs in energy efficiency, and this is where Yayuan's work is really focused. It's possible we might be able to scale the current technologies today, but given the amount of energy you need, I think we really need a step change improvement for it to be viable long term. Another thing to consider as well is that we need plants that are 20-year plus lifetimes. That's needed so we can amortize the capital costs, right? And so if you're going to spend $1 billion on a plant, you want it to run for a very long time, and you want it to run nearly 24/7. That way, you sort of levelize the cost of building that out over time. And of course, you need all the manufacturing, right? And so if you're going to build a 1 million ton scale DAC plant, you have to have all the materials, the supply chain, all that worked out for building that out. And so academia and startups and things are really focused on, I think, the technology column. And then where companies like Total and other industry companies really can help is on the deployment side, right? And so I already mentioned that one of the key bottlenecks is having a place to put the CO2 that you capture. Obviously, we're working on building out that infrastructure for transport and storage. Another key concern is the energy supply for DAC, especially with today. You've got AI, needing a ton of energy. You've got electrification in general. So DAC has got to compete for those same kind of clean electrons, right? And so at least for the foreseeable future, 5 to 10 years, that's going to be a challenge. And the final one is policy and public acceptance. And as a scientist, I often don't consider that aspect enough. But obviously, nobody's going to spend billions or trillions of dollars unless they have to, right? And that's just the honest truth of it. There's a lot of work being done, especially in Europe, on the carbon trading system and so on. But we really need firm policies in place that industry can make these big dollar bets that's going to make sense over a 20-year timeline, right? So we need a pretty firm commitment from governments. And the other aspect too is public acceptance, right? And we need, most likely we need pipelines, which most people do not want in their backyards. So that's another important aspect that has to be overcome. So the point is that, the research is critical for improving the technology, but, scaling this up really has to address all these different aspects. So electrochemical. So yeah, we sponsored the research project with Yayuan. Electrochemicals is a very attractive approach for doing DAC, right? And so we're still looking for those breakthroughs in energy efficiency and stuff that we think is needed for large scale long-term deployment. And so, a lot of the current methods that people use for DAC are thermal based. There's a lot of thermal losses and stuff. Electrochemical allows you to take electricity kind of directly to the CO2 capture and release mechanisms. And so it has a potential to be a lot more energy efficient. And of course, you can envision a system that is all powered by green electricity, operating off of solar or wind, and could be a long term a much more elegant way of solving the DAC scaling problem. All right, that's all I have. Thank you.
Amazing talk, Jeff and Yayuan. And it was really great to see them in succession to sort of go from the very fundamental cutting edge science that Yayuan is doing to a very broad, high level industry perspective of the technology as a whole and the barriers. At this point, I'm going to open up the field questions to field questions from the audience. If you have questions, feel free to leave them in the chat box, or if you would like to just raise your hand and ask your question directly, that is also totally okay. So yeah, are there any questions?
Um, I guess on the 45Q tax credit, I thought that was $85 a ton, not $180 a ton.
Yeah, 85 is for point source capture. So if you capture CO2 from a cement plant,
okay,
it's a lower amount.
Yeah.
So I have a question.
Yeah.
My name's Denny Ma. I'm a retired chemical engineer, electrochemical engineer from DuPont after 40 years. So I have three questions. One, what type of anion exchange membrane was used in this work?
Yeah, so we use the commercially available anion exchange membrane, Sustanion.
What brand?
It's from dioxide material. It's called Sustanion.
Okay. In the performance versus time, didn't look like there was any scale. Is that minutes, weeks, years, months?
Yeah, I apologize. So that long-term cycling was over the course of 50 hours, I believe.
50?
Yes.
Okay. Are you considering any kind of air pretreatment? There's more than air, than nitrogen, oxygen, and the CO2. There's contaminants.
Yeah, we didn't test the real air. We used synthetic air, but at this point, I think they should be pretty. The electrochemistry is insensitive to the so-called contaminant for air case, but particulate matters might be something depending on the location where it's implemented. We might need to remove that to prevent any clogging
Because
of the yeah.
You're showing lifetime for I think the membrane's 5 years, maybe?
Mm-hmm.
Yeah.
Yeah, that was the assumption. Yes.
Yeah, that's a lot of material in 5 years.
Right. Yeah. So
Going into a porous structure.
right. Yes. So that's what we were expecting. Particulate matters might be important to be removed before we send it to the electrochemical reactor. But yeah, so some more longer term stability test with real air is important. So yeah, it's a good point.
Well, I'm just gonna, encourage you to, keep doing the work, but there's a lot more than just the electrochemical part
Yeah, I hear you.
for a whole system.
Yeah.
Thank you.
Thank you, Denny. Andre, I see your hand up.
Yeah, thank you so much. I mean, this was a really, really great talk from both of you guys. I really enjoyed it. This kind of interface, I mean, between industry and academia and working together towards this common goal is something that we fully embrace. And I guess my question for you guys is, given the current landscape, what are things that, perhaps we could do as a center? Because as we bring people together looking at these technologies, what are things we can do as a center that could be more proactive in driving this forward? And what are some of the barriers that you guys see, I guess, in terms of the driving force that's moving this promoting direct air capture and putting that together.
Definitely.
Yeah. Yeah, I think, I mean, yeah, my position is that there's still several breakthroughs, key innovations needed for DAC to be viable, long term, right? And so, and I think academia is the great place. I mean, to identify those innovations, and I think that there already kind of exists a ecosystem between industry and academia. I'm sure there are ways that can be improved. The other side of this too is the policy and regulatory side, which drives a lot of the funding that goes into research and so on, right? And with the current administration and the lack of emphasis on CO2 capture technologies, right? And so it makes it a little bit tougher. So, I mean, it's sort of the whole system, right? It's government, industry, academia. Getting that alignment is what's key.
Yeah, and I guess in terms of that with as far as having our center together and promoting that, do you feel that, I guess, what's the driving force now that's really driving direct air capture? Is it momentum that's carried over from previously, or is there what do you perceive as the main driving force that you see that has a company like Total interested in direct air capture?
Yeah, I think, I mean, obviously the momentum has slowed, especially here in the US, right? Europe still has their ETS, the cap and trade system for CO2. So there's still policy incentive there, but the framework for actually using DAC, CO2 credits from DAC, isn't firmly established yet. And so I think everybody's still seeing DAC as a long-term solution, but the pieces aren't really in place to make big moves in terms of deployment.
Hmm. Thanks.
I'll come to you, Ian, but I'm gonna go to some questions in the chat. So from Avinash, have you tried Nafion-like ionomers for the interposer and utilized principles from electrodes fabricated for low temperature PEM fuel cells?
Yeah, those are great questions. So we need our cathode to be anionically conductive, so it has to transport hydroxide selectively. So that's why we didn't use Nafion, because it's opposite charge. But the rest of the cell is basically very similar to the fabrication of low temperature PEM fuel cell, how we assemble the components together and the counter electrode and whatnot. So yeah.
Great. And then is there a reason, this is from James, is
Mhm.
there a reason for using a 20% sweep gas instead of purifying directly?
So because the system is small, so we use the low flow rate carrier gas for the regeneration state so that we can just more accurately quantify how much CO2 is being produced. But we also demonstrated release of pure CO2 without a carrier gas, and there's no problem. We can do that. So because of the interest of time, I didn't go to a lot of details, but the paper is on archive. So if you're interested in reading through the supplementary information.
Great. Let's go to Ian now.
Hey, Yayuan.
Hey.
Nice to see you again. I have a question about your AEMs and things like that.
Mhm.
So it seems like Sustainon is still the one everybody's using, huh? That's like the still like
Yeah.
kind of like the benchmark, yeah.
CX needs to help us out.
I think Aowen's somewhere in this chat, so she might be able to help too.
Oh
But
yeah.
one thing I think about now, because I work on coatings, is there potentially a way you can think about maybe coating these things with a thinner layer of an AEM
Yeah.
on some kind of porous, GDE or something like this that would get you probably, I would hope, better transport of these ions through. So maybe it'd be less gunking and things. I know you're still doing the basic research. You're not thinking
Mhm.
about this huge scale up yet because but maybe that's something to think about too.
Yeah, I think that's a great idea. Like, we don't have the fabrication capability to do that, but ultimately, I think a dense, like thin AEM layer on top of a porous interposer would be an ideal design because we really don't need a thick AEM layer to do what we want. So that kind of decrease the transport resistance overall. And yeah.
Yeah, and I think that would help with your driving more of your current density, so you can get
Yes.
more faster reactions, right? And so you wouldn't
Yeah.
have to worry about that. Yeah. Okay.
Absolutely. Yeah.
Okay. Thanks.
Okay, I'm going to return to the chat real quick. Are any challenges you encountered while developing the ion exchange wafer and interposer design? From Michael.
I think this is and the interposer is taking inspiration from electrodialysis field where they already use kind of this kind of bind ionomer resin wafer to do their work. So this is actually good because we have a monolith of interposer that can be put into the electrochemical cell, and that actually increase the reproducibility compared to if we just put resin particles into the cell. But with that said, I think some long-term aging studies to look at this stability is important that we haven't done. And also, how do we make them into a larger scale with good uniformity? And if we can make them even thinner and more porous with still maintaining the mechanical robustness, I think those are questions to be answered.
Great. Okay, continuing in the chat, using pulse voltage profile, decreased carbon capture efficiency in a low current density regime, which is showing different trends from the high current regime. Do you have any idea on why you saw this trend? And can you also please explain the time scale and applied voltage for the pulses? This is from Sung-Soo.
Yeah, I think for low current operation, the rate limiting step is probably not the CO2 solubilization into the liquid phase. So that's why I think with pulse, the overall hydroxide concentration is lower. So that's why a lower operating current, you kind of compromise the capture efficiency. But maybe that's something that the Justin can further help us to understand with a better model, which Justin is trying to help us out. The voltage is we were doing the constant current pulse. So we just current on and current off, and the time scale is on the order of 10 seconds to 30 seconds, that kind of thing. Yeah.
Perfect. And then one more question for Yayuan from the chat, then we'll move on to Matthew. What is the concentration of the KOH electrolyte on your cathode side?
So the cathode is, we're not using any KOH, so it's the local hydroxide being generated at the air electrode interface using oxygen reduction from air. We would expect that to be a highly alkaline because of this then reactive hydroxide generation region.
All right, great. Matthew, you want to?
Yeah, please. Yeah, Matt Mayer from Helmholtz, Berlin. Very nice talk, nice work, and yeah, nice to meet you. Finally online. I had a question maybe on the idea, I guess question for both of you about the system design, whether it should be continuous or like decoupled. So obviously, Yayuan, you're focusing on a coupled system that does the capture and release like continuously. Whereas we see some carbon capture companies that are doing electrochemical methods that they show some advantages of decoupling, where you can separate in time and have a different kind of reservoir storage for capturing when it's, yeah, the sweet spot for that. So maybe can you say something about that? Do you see that the continuous mode has key advantages, or is it still not clear if it's better to decouple or couple the steps?
I know Jeff has something.
Yeah, I'll take this one. Yeah, so I mean, there's a trade-off there, right? I think it's an attractive idea that, especially if you're using intermittent renewables, right? If you could do the energy-intensive steps of DAC when electricity is dirt cheap, right? The challenge with that is without doing continuous, you may not have the utilization rate that you want to justify plant costs, right? And so, if you're operating only 30% of the time because you're only using intermittent renewables, that greatly inflates your capital costs as they get levelized over time, right? So, I think it's an interesting concept. I think you have to think about energy storage as well. I think ultimately you do want as close to 24/7 kind of continuous operation. Whether you can get there intermittently, right, is a different question. But yeah, it's definitely an engineering cost trade-off, I think, on which way to go.
Okay, we'll go back to the chat. There are some questions for Jeff. So first is, how is Total thinking about DAC versus point source capture? It seems like your existing integration would give you an edge in point source, and Shashwati is curious about how that affects your priorities.
Yeah, I mean it's way easier to not emit the CO2 or capture it at the source where it's concentrated than trying to capture it once it's diffuse in the air, right? And so, and that translates to energy consumption and cost as well. So, most point source capture technologies are in that kind of $80 to $120 per ton range. Just kind of give you an idea, whereas DAC is roughly 1,000. And so, for us, the most cost-effective solution is to either not emit it, so replace something with electrification, for example, or capture it at the source. That said, DAC is still needed for any residual emissions that you still have, which you always have some. So that's sort of the priority, right? Is the low-hanging fruit first. DAC is kind of at the end of that process.
And then what's your opinion on the other, this is from Tamino, what's your opinion on the other available EChem carbon capture systems like EMAR or quinone based? And where do you place this alkaline based approach, specifically in terms of energy consumption, efficiency, scalability, and long-term operation?
Yeah, so they're all interesting concepts. EMAR is very focused on point source capture, right? And so that's an interesting area that we're monitoring. For DAC, I mean, yeah, the challenges with electrochemistry, and I used to be a fuel cell electrolyzer guy, so I know this firsthand, is that they use very expensive materials. The stacks themselves are very expensive, right? And so getting costs and cost down, durability up is going to be one of the main challenges for electrochemical approaches. So like the quinones, for example, if you're using that in a DAC process, it's exposed to air, it'll degrade over time. That affects your cost and replacement cost and so on. And so I do think that long-term electrochemical is a very attractive approach, but it does have to address all the cost and durability concerns.
And then we have another question for Yayuan. From Wojciech. I have a question for Liu. I suppose that the contact area between your interposer and air should be maximized. How do you envision this electrochemical cell to be scaled up with that factor in mind?
Yeah, so the contact area is where these microporosity, the interposer layer is actually doing. So for scale up, it's going to be just coupled with like a gas diffusion electrode and the interposer layer. So yeah.
Great. And then there are two questions left for Jeff. We're curious about whether, from Vu, if Total is interested in CO2 conversion to fuel and other products as well as just capture.
Yeah, that's an active area that we're sponsoring a lot of R&D projects on. So including electrochemical approaches, right, for converting CO2 to the various feedstocks. I mean, again, I think that's part of the long-term vision of a kind of a net zero society in the future. The current processes are very energy intensive and therefore expensive, right? But that's what we're trying to drive the cost down. I think it's going to be part of the mix going forward.
Great. Maybe we'll just end with Hui is raising his hand, so maybe we can end with that question.
Yeah, sure. Sorry, I think my camera has a problem. I cannot show my face, but my question is for Dr. Liu. First, for the AEM, I have been working on AEM for a long time, especially working on a very effective AEM electrolyzer. I would suggest you contact with Professor Yusan Yan from Versagen. They have much. I just spoke with him yesterday for other projects. They have much better.
Yeah, we're familiar with Yuzhan's membrane. Yeah.
Yeah. Actually, and my real suggestion is all the AEMs. I don't think they are stable. Also, they are very expensive. I'm wondering whether you have using alkaline just system to conduct your work. My understanding that the alkaline system, right, is more the frame is more stable, also easy to perform. The most importantly, you can eliminate the poor stability of the AEM, and then you can focus on your work. So this is also easy to perform. This is my question.
So I might not. So you said should I use or should I not use
I
alkaline
am
system?
wondering why you have used the alkaline
Alkaline. Yeah. Good.
system. Basically, use diaphragm instead of using EM. The reason I asked is because diaphragm, the system obviously is more stable, right, than the AEM system. Yeah.
Yeah, that's a good point. So the main thing is the interposer layer. So I would, yeah, that's a good suggestion. We might be able to replace the AEM with a diaphragm system if we can somehow prevent the flooding of the electrolyte into the interposer, because we would need to make like a non-flooded parts interposer layer for sufficient gas contact. But if we do a smart interposer design, or as Yan suggested, using like a denser polymer layer at the depths of the interposer, we might not need to use the AEM. You're right. Yeah, that's something for future study.
Yeah, thank you.
That's a good suggestion. Yes.
Great. Well, with that, I just want to say thank you everyone for coming. We had a really great turnout. Seems like people are very interested in electrochemical carbon capture. And we'll continue to do seminars like these as a part of DC-MUSE, so keep an eye out on LinkedIn. And again, thank you for everyone for coming and for the engagement. Really great questions and everything. Perfect. All right. Bye-bye, everyone.
Thanks. Bye.
Thanks. Thanks so much, Jeff. Thanks,
Thank you,
everyone.
Jeff. Thank you, Yayuan.